Do you want your ARM microcontroller to be as fast as Lucky Luke dueling his shadow? Let me show you how to do this. Before we start, I would like to invite you to my Discord server, where we can discuss many topics related with ARM Cortex-M cores, embedded systems, and overall programming. Links to the server in the description under the video. Now, straight to the point. There are 4 possible clock sources that divide into 2 groups, internal and external. Internal means they are built into the microcontroller by the vendor. External means user can connect his own clock source. Each of these groups contains 2 clock sources, high speed and low speed. High speed sources are meant to be the main clock source for the whole system. Their frequencies may vary on each microcontroller, but most times they are around a few to a dozen megahertz. In our case, these are 16 MHz for high-speed internal and 4 to 26 MHz for high-speed external with 25 MHz external oscillator mounted on the board. Low-speed sources are a quite different story. They are meant to provide a clocking signal mostly for watchdogs and real-time clocks. These clocks are not used as a system source clock. Now, you might ask why to use an external clock source if there are already internal clocks provided by the vendor. The answer is simple: quality. Although the internal oscillator is free and built-in, its accuracy is very bad. Looking into a datasheet of the microcontroller used on the Blackwell board, we can find that built-in high-speed internal RC oscillators' accuracy is affected by temperature and may range from -8% in -40 degrees Celsius up to 5.5% in 125 degrees Celsius. This can be trimmed down to 1% accuracy by some runtime measurements and calibrations, but it is still quite a lot when the target application is highly dependent on the source clock frequency. On the other hand, we have a possibility to use high-speed external source clock. And yes, we need to spend money on them and dedicate some PCB area close to the microcontroller, but we get a highly reliable source clock with accuracy measured in parts per million. This means that we get an accuracy that is at least 1,000 times better than the accuracy of the built-in HSI oscillator. Looking on the Blackwell board, we have a 25 MHz, 9 pF oscillator. I found a similar or even the same oscillator and checked its frequency stability, plus minus 10 to 50 ppm, which is equal to 0.005%. I hope you get the point. We may have multiple clock sources in our system, but we can use only one at a time. To select which one is used, we must configure System Clock Multiplexer. And here we can see there are 3 clock sources that can work as system clock source: high-speed internal, high-speed external, and PLL, which stands for Phase Locked Loop. But what is PLL? Let's have a look on what Wikipedia says. PLL is a control system that generates an output signal whose phase is related to the phase of an input signal. This doesn't say much, but if we read the application section, we find PLL is used to synthesize new frequencies, which are a multiple of a reference frequency with the same stability as the reference frequency. Aha! So in other words, in our case it is a frequency multiplier. This means we can multiply the reference frequency and get even higher system clock. Awesome! Okay, so if you have to pick from 16 MHz HSI, 25 MHz HSE and higher frequency PLL, then it's an obvious choice and we want to run our system with the PLL as its source clock. But how do we do this? First, we need to configure the PLL itself. We know that our microcontroller can run at up to 100 MHz and we want the PLL to output this frequency. As an input from 2 available reference clocks, HSI and HSE, we select the latter. Next, we need to configure multiplication and division factors to get 100 MHz output. In case of STM32, tool provided by the vendor is able to calculate these factors based on target output value. And so, with the help of STM32Cube-MX, we get M factor equal to 12, N equal to 96, and P factor equal to 2. Now, to apply these values in the microcontroller, we are going to use reset and clock control module and its PLL configuration register. This register has several groups of bits with different meanings, including PLL source and all factors. There are also groups of reserved bits that we are not allowed to modify. In the previous video, I have already showed you how you can modify registers using peripheral classes with properly defined members. In this video, we will define some unions and structures to make access to these members easier. Starting with PLL configuration register, first we define a union. As its members, we define 32 bits unsigned integer variable named value and an instance of PLL configuration bit structure. Of course, we also have to define bit structure itself, and for this we are going to use bit fields. This will ensure that all members occupy proper amount of bits. Also, we must remember that we are not allowed to modify reserved field, so we make them const. And to make sure there's no padding added to this structure, we give it a packed attribute. With the union defined like this, we are able to access register by 32 bits word or by separate bit fields that are part of it. As the union is private, we also need an interface to modify values, and for this we implement two functions, one for setting PLL source clock and one for setting PLL factors. We also need some enum classes and a structure to avoid writing invalid values and avoid mess in the code. Using approach like I just showed you, we are able to implement unions and functions for all the actions required to run the microcontroller at 100 MHz frequency clock. And that is configure PLL source clock and factors, which we just did. Set prescalars for AHB, APB1 and APB2 buses. Enable high-speed external clock. Enable PLL. Set PLL as system clock source. As Cortex-M developers, we must know what are the buses that we set prescalars for. Here we have AHB, which stands for Advanced High Performance Bus, main bus in the whole system connecting core with flash and RAM memories and all peripheral blocks. APB1 and APB2, advanced peripheral buses that provide connection with peripherals available on the chip. Let's implement missing functions. As for setting buses prescalars, I already implemented struct for the RCC clock configuration register before, and here we must now add public functions to set prescalars. From the datasheet, we know that AHB and APB2 buses can run with 100 MHz frequency, so we set prescalars for these buses to 1. APB1 bus can run with up to 50 MHz frequency, so we divide the system clock by 2. Now we can enable high-speed external clock using RCC clock control register, but before we continue, we must wait till the system indicates an oscillator is ready and stable. This also means it is ready to use as a reference clock for PLL. We have already configured HSC as a source clock for PLL before, and now we can enable PLL. Also, this time we have to wait for the indication that it's ready and stable. And now the final step, setting PLL as a system clock source. For this we again use RCC clock configuration and its system clock switch bits. We select PLL by writing bit value 10, we wait for system confirmation, and voila! We now have a microcontroller running at its full speed of 100 MHz. If you enjoyed this video, hit that like button, and if not, leave me some feedback and tell me what you didn't like. You can also go to my GitHub repository, download the source code for this video, and play with it on your own. Please don't forget to subscribe my channel. Thanks for watching, and I'll see you next time.